All right, guys. So anything from the quiz besides that? That one? All right. So that's the main thing. There was figuring out the right value for x, but you know, some people made some mistakes in here too. Okay. Anything from homework stuff? Oh, look, double digits. All right.
Are we going to continue off where we left off last time with optimization?
Say all that again.
Are we going to continue off where we left last time?
Oh, yeah, definitely. Okay. And I put the quiz statistics up here if you want to see where you kind of fell. Does anyone need that optimization sheet from last time?
Is that the one we did on Monday?
Say again?
Is that the one we did on Monday?
The one that we started working on Monday.
Yeah, Monday. Yeah, I don't.
You got it? Okay. Let's see now. Let me try to get us back to where we were. 1A, we set up the rectangle, and then we identified variables, and it told us the area, so they tell us the area is 180 square feet, so this would be, that's the equation that they tell us. B, they give us some cost stuff. Can somebody remind me which thing did we call the special side last time?
The top one?
The top one, okay. And that's the special, and again, it was $45 per yard, 45 divided by 3 feet, $15 a foot. So this side is $15 per foot, blah, blah, blah. So this would be 10, 10, 10. And again, I really, when you look at the question, it says, if it said find the minimum shoe length, what equation do you want? You want an equation that tells you shoe length, right? So this says find the minimum cost, so I need a cost equation. And what will the cost equation be?
25x plus 1.
Yeah, 25x plus 21. There you go. So you got to make sure that the equation you're going to take derivatives of, in this case, is a cost equation because I'm trying to find the minimum cost. You wouldn't do the perimeter and start doing derivatives. It didn't say minimum perimeter. I like it, maybe. Okay. So now what do? This is what they ask us. This is what they tell us. How do I work with these? How do these work together?
Substitution.
I can't remember. Did we pick a letter to solve for last time?
Not yet.
Oh, yeah.
X? Okay. So if I solve this for x, divide by y, I get x is 180 over y, which is really good information. So again, this is, I've talked about this before. This idea is, I build it from pre-calculus, so I have no idea how people teach pre-calculus. But again, the more you can break a math problem into parts. So the first part of these problems is, what do they tell me? What's the equation for what they just tell me? And then what are they asking me? Well, how do you find that? Look at the question, right? Make an equation for that. And then what's wrong with this equation? Too many damn variables. So now I can replace the x with this business. Now how many variables is C a function of? One. Yeah, it's a function of y. That's it. Let me stop for a minute. So that pretty much catches us up to where we stopped, and then this was the next step. Like it. Now what the hell do I do?
Solve for what?
No.
No, bridge.
What are we trying to find?
Cost. Minimum cost?
Minimum cost. How do I find the minimum
Oh.
of a function?
Take the derivative.
Take the
derivative.
There we go, right? So all of this was just trying to make a problem like in section 4.1. Now that we've set this up, we're back in section 4.1. It's just they didn't tell us the equation. We had to make the freaking equation, right? Now it's just find the minimum. Take the derivative, set it equal to 0, or where it's undefined, and blah, blah, blah. All right. What do I do? Let's see, let me follow. Solve the area equation. Who cares? That's what we just did. So this is part C. And then D says find the critical numbers. So what is the derivative of the cost? And what am I taking the derivative with respect to? Why? 11, because that's the freaking variable, 11. So what is the derivative? Well, let's see, let's clean this up a little bit. What's 25 times 180? That would be 50 times 90. You guys know that trick?
It's 4,500.
4,500? So what is the derivative of this?
Can we do
You like-
negative 4,500?
Good. This is
Yeah.
y to the negative 1. So it'll be negative 4,500 over y
To the negative 2?
squared. Right? It's already on the bottom.
Oh.
So you could rewrite this like this. Right? So when I take the derivative, it'll be negative 4,500 y to the negative 2. And then this, of course, is just
What, like 20?
20, 11. What do we want to do? What do we want to do?
My minimum cost
True. So what do we want to do with that?
and the critical numbers?
Critical numbers, all right? So what's one critical number that screams at you immediately without doing any work? 0. Is 0 a valid answer? If I make this side 0, what would the area be?
A line,
It would be a line, so what would the area be?
0.
So screw that, right? I throw that out because this is a physical problem. So I can always throw things out that don't make physical sense if I'm in a physical problem. If they had just given me this equation, that would have been a valid critical number. Why is that something I don't consider? Because it makes the problem not make any sense in the real world. I like it. In fact, it would lead to a, what do you want? A situation where I have no area, so I don't know what else to say about it. How do I find the other critical number?
Make it equal to 0.
Yeah, make it equal to 0.
So
This is where it's easier to look at it like this. Go ahead, sir.
you could then change it to like 4,500 over y equals 20. So you could, I think these are make 0.
Yeah, I would, you can subtract the 20, the negatives cancel anyway, so you end up with 4,500 over y squared equals 20, is that cool? Right, subtract 20, negatives cancel, or just add the other guy. How do I solve that? What sucks about that problem? What's the worst thing about it?
The y's on the bottom.
Yeah, so how do you take care of that?
Multiply.
Yeah, there you go. So the beautiful thing about equations is if there's something about the equation you don't like, you can very, very often kill it. I don't like that, or kill it. Now there's no fractions. Now it should be easy as shit. Maybe? Is it? Divided by 20.
Take this one.
Square root. And you get?
Plus or minus 15?
Yeah, plus or minus 15, and of course, which one of those makes no physical sense?
Negative.
Yeah, if you get me negative 15 feet of fence, I am not gonna come see that, because I don't want, you get sucked into another dimension, I don't know what that means. So again, we've thrown out various critical numbers just because of the physical nature of the problem, right? Now, what would I do to make sure that that's an actual minimum?
Not in the sign code, right?
Yeah, you could. Let's see. So I got my 15. I'm not going to care about, so I'm going to stay close to 15. Did we throw out 0? Did we throw out negative 15?
Yeah.
So they would show up on the official sign diagram, but I don't care about, I'm going to stick close to 15. So if I throw in let's see, if I throw in a 14, what does this become? Well, let's see, let's throw in a 10, that's easier. You guys with me what I'm doing here? I just want to see if it's going, I want it to be going down and then up, right? So if I throw in a 10, which is on this side, correct? Throw in a 10, it's 100, so it's negative 45 plus 20 is negative. Right?
Yeah.
And if I throw in a 20, that's negative 4,500 divided by 400, which is 45 divided by 4, which is about 11 plus negative 11 plus 20 is positive, bang. So is this a minimum?
Yeah.
Yes. So what does that mean?
Is the minimum cost. It's the minimum cost.
Is 15 the minimum cost?
Oh, no.
What is 15?
Feet.
15 is Y. Yes? Good, so that's 15 feet for this side. So what is the question? It says find the minimum cost. Do I have a cost function that just cares about Y?
No.
Yes.
Yes. Couldn't I just throw 15 in here to see what the cost is, right? Yes, see what I'm saying? So again, it's you set up the equation, they tell you something, they ask you something, you set this up, and you use what they tell you to help with what they ask you. Then you're back in section 401. Find the critical numbers, make sure it's a min or a max or whatever it is they want, right? And then answer the actual question. So the question wasn't, what are the dimensions? The question was, what's the actual minimum cost? And you've got your equation. So now we can just put in 4,500 divided by 15 plus 20 times 15,
That's 600.
600. Good job. Okay, freak it out. Now real quick, I'm gonna push this just a little. That's done, right? That's done. That's done. Right, and I'm gonna do the thing you guys love. I'm gonna go one little step further. Remember what I said? If I have a rectangle, what shape will maximize the area for any given perimeter?
Square.
A square, right? That's just perfectly the sweet spot, right? Did we come up with the square on this problem? If y is 15, I'm gonna do extra stuff, it's not what it asks. Y is 15, so what is x? Can anyone tell me what x is?
12.
Y is 15, x is 180 divided by y. Is that 12? Yes. Feet. That's not a square, correct? But watch this, watch this. This is so cool. How much does this side cost?
15.
15 times 12, which is
180.
180. So this side will cost 10 times 12, 120, right? Are you guys with me? Okay. How much does each of these sides cost?
10.
15 times 10, 150, 150. What's the total cost in the x direction?
$600.
No. Total cost in the x direction.
300.
300. What's the total cost in the y direction?
300.
300. So there's sort of a square hidden, but it's by cost. All right, that's pushing it. That's pushing it. I kind of love that the square sort of still shows up a little bit, but that's more than you have to worry about. Okay. So again, right at this step, we're back in 4-1, right? Right at this step. The whole point of a word problem has always been you set up your equation and then you do the same shit you did earlier when we just gave you an equation, right? If you think back to algebra, that's pretty much, here's how to solve an equation. Now here's some word problems. And that's where you have to, they don't give you the equation, you have to create it yourself, right? And that's always, of course, should be the hardest part. Did we do, there, did we do the, we didn't do, did we do the one on the back? No.
I'm still doing the first one.
Yeah. So turn that over, look at number 2. So this is a different kind of problem. Let's see, we've done this kind of problem sort of before we've set this up. Let me see if you guys try to do part A on number 2. Does anybody need this worksheet? to do 2a. See what you can do. Can't do anything, just be patient. Yeah.
So do we make an equation for this or?
Total. Yeah, otherwise you can't do shit. I don't know if you guys remember doing this kind of problem before. We set this up, what was it? X squared minus 1 here. So I mean, if you wanted to, you do a quick sketch. Maybe your sketch will even be better. It's a really good idea. When you're dealing with something graphical like this, you do a quick sketch. Can you guys see, could you draw, if you did this sketch, could you draw in like the answer to this question? You guys see what I'm saying? What's the closest? Can you draw a line between these two, this function and this, that would be the closest, that would be the shortest distance, right? Would it be this? No, it's gonna be, can somebody describe it to me? What would it? Sure, diagonally. And the funny thing is, it's gonna end up being perpendicular to that point in a way, right? That's the closest, yes? Maybe. So that's the idea. This doesn't really immediately help, but it does help because what is this point right there? That's the answer, right? What is that? What is that point?
2, -1. Wait.
Nope, that's 2, -1. Right? What is that point? And I'm not looking for numbers because you can't tell me numbers because that's the whole point of the problem. So if you can just see it, then you're done and that's crazy. All right, I'll help you out. I mean, what is this? Do you know? So what is it?
X.
X, good. And what's the y value for any point on this function?
X squared minus 1.
X squared minus 1. Any point on this function, if you know the input, the output is that squared minus 1. We've done this before. So if I write this as a point that this goes through, it's not specific enough because it doesn't just go through any y. If the input is x, the output must be x squared minus 1. Do you guys see that? Why does this help me? Because what's the distance formula between 2 points? Didn't I make a little triangle here? It's just Pythagorean theorem.
Is it change the y to x?
No, that's the slope. No. So if I have 2 points, and I want to know this, what's this? No, be better than that. The change in y, right? So it'll be y2 minus y1. What's this? x2 minus x1. Is everybody with me? This is the x direction, this is the y direction, yes? So you're back there saying what's I said, but if I wanted to make slope, I would do the ratio of those things. That's not what I want. What old Greek dude comes into play? Pythagorean, right? So what's d squared? It equals?
Y2 minus Y1 squared.
Yes. I'll do this one. So somebody out there should know that the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. And all I did was squared reason we do that, would you want to do derivatives on this function? No. I'd much rather do derivatives of that function, right? There's no chain rule up there. And why does it make sense? If I minimize d squared, doesn't that mean I've minimized d? Okay. So let's put some more information in here. Help me out. So let's treat this as the second point, right? What goes here? X minus 2 plus x squared minus 1 minus negative 1 squared. There are a few problems in the homework that involve something like this. Right? It's also called the closest approach. If I see a comet coming, what am I really curious about? It's headed towards Earth. What am I curious about? How close will it get? So this is the kind of math you could do if you knew the trajectory of the thing and you put Earth at a point and you have the comet coming, you can figure out its closest approach. Yes? Really good to know. If it's 8,000 kilometers, that's actually a problem, right? But if it's 1.2 million kilometers, you're like, okay. Because, yeah. So if I clean this up just a little bit, what happens in here?
X's cancel out.
So you x2 then. 4. Okay. And here's something interesting that I really, all right. There are several types of problems in this section. One type is the one we did first. They give you an area, they talk about the perimeter or whatever, right? Another type is a graphical type, like this. And then we'll do another one here in a minute that's another kind of general type. So one thing to notice about this, what's really beautiful about this, if I minimize d squared, so d squared is a function. I don't have to do implicit differentiation. I don't, because I'm thinking of d squared itself as a function. So I'm going to just take this guy's derivative. What would that guy's derivative be? Because now I've got this is the function that, what am I trying to do to this function? What am I trying to do to this function? What does it want me to find?
Square distance.
The minimum square distance, right? So of course I'm going to take a derivative, find my critical numbers. We're at that point now. So all this was the setup. This is like truly section 4.7, and now I'm at section 4.1. Take a derivative, find the critical numbers. So what's the derivative of this?
2x minus 2
Yeah, 2x minus 2, I like it.
plus 4x cubed.
So I get 2x minus 4 plus 4x cubed. So what do I want to do with that?
That equals 0.
Yeah, set equal to 0. It's obviously not undefined anywhere. Let me rewrite this a little bit. 4x cubed plus 2x minus 4, and I want to set that equal to 0.
Take it 2 out.
What's kind of wrong with that? Can I attack it with like quadratic formula or something? Why not? What's wrong with it? Is it quadratic? No, why?
The powers are.
Power's the third power, right? If only that was a squared, we could attack it. One thing I could do is divide by 2, yes?
Yeah.
Might as well. Do you guys have any idea where to go from here? Oh, holy shit. All right, sorry. I didn't mean it. Yes, synthetic division is a good idea. I can't remember, have we talked about synthetic division here yet? Okay, this might be why I created this problem. It's kind of coming back to me. Synthetic division is stupid powerful, right? Synthetic division, how many here remember hearing about synthetic division sometime? the rest of you are like, you're just making that word up, aren't you? No. So I should have brought that over. All right, this is where you got to really reach back to your pre-calculus. What are the possible, let's see who kind of has a adverse reaction to this race. Possible rational roots.
Oh
I want you to realize, if I was able to factor this shit, yes? Blah, blah, blah. What would these numbers have to multiply to be? Whatever numbers here, here, and here, what would they have to multiply to be? -2, yes? I like it, right? So obviously, it'd be plus or minus 1 or 2, those are possible roots. Because if this is like x, if b is 1, this is x minus 1, then 1 is a root, yes? But, this stupid thing, help me out. What if this one was 2x minus 1? What's the root of this? What's the root of this? X equals 1/2, yes? So I got to divide by the factors of the first thing. Does that ring any bells? I don't know how long it's been. I think I know. I don't think, yeah, the people that fill out the survey, most of you said it was decently recent that you took pre-calc. A few people said it's been more than so many years, and I feel for you. Right? So hopefully, so let's see. Plus or minus 1, 2, that's divided by 1. 1 over 2, and 2 over 2 I already got. So this is the complete list of the possible rational roots. Okay.
Right, so P is the factor of like the first coefficient?
Say again?
How does it go again?
Yeah, this is the
P over
the
Q.
factors of the last number
Okay.
divided by the factors of the first number. And then you put them together in all the different ways you can. So I don't know if those of you that remember this, that's a very short list compared to what it could be in general, right? Yes. And then you got the Moivre's theorem, and you got open and lower bound, you got all this shit, don't worry about it. So how does synthetic division, so I could do, all right. No, I can't erase you, you're important. I could do, what I'm trying to do, if this sucker factors to be something times something times something, couldn't I divide by one of those things to see if it goes in evenly? So synthetic is a way to do long division of polynomials quickly. So here's how synthetic division works. Can somebody pick out a number from here?
1.
1, I love it. Put him in what I call the penalty box. Right? I don't really watch hockey, but what the hell? Little penalty box. Can somebody read off to me all of the coefficients of this?
2.
2.
0.
0, good. Because what is that the coefficient of?
Two-
X squared. Keep going.
-2.
Okay. Does this look familiar to some of you guys? Yes? And again, I'm considering doing the long division just to show you how it matches up. So the way this works is you bring the 2 down. 1 times 2 is 2. Add. 1 times 2 is 2. Add. 1 times 3 is 3. Add. This is the remainder. Did it go in evenly? No. So that didn't work. Right, so let me keep track of this. We got 1, 2, 1/2, -1, -2, -1/2, right? 1 didn't work. Okay. I don't know if past Jeff made this work. This might be remarkably frustrating. I don't know. So you guys try, pick another number for me, somebody.
2.
2, real quick, try 2. And let me see. That will definitely not work. 2 does not work. You can see really quickly. Bring the 2, that's 4. 0 plus 4 is 4. Times 2 is 8. And it's not going to work. Can you guys see that?
What are you doing?
Okay, so let's cross 2 out.
Holy shit.
Yeah, let's try 1/2. Let's see. 1/2 looks like it might work. 2. 1/2 times 2 is 1. 1. 1/2 times 1 is 1/2. No, let's see.
1.5.
1 1/2, so that's 3 halves. times 1/2 is 3/4, that doesn't work. Right? So none of the positives work. Wow. So what about the negatives? Let's see.
No,
Yeah, -1,
doesn't work.
-2, 2, yeah, that doesn't work. -2, okay, so this is what this one is. Okay, I see. So how do what's the last resort then on this? Since it looks like synthetic doesn't work, the last resort on this would be to solve it graphically. All right, does everybody have their graphic calculators if you want to play along? Okay. I think past Jeff just made this a great opportunity to review some stuff. It's me. All right, let's see. Okay, oh. Now, if I put this problem on a test or something, I would tell you to use a calculator if you needed to, or I would tell you don't use a calculator, meaning it should factor. You guys with me? Okay. Because otherwise you go insane if you're not there already. Are you gonna wake up, little dude? No? Okay. I have a vague memory of trying this and it didn't work before. Oh, well, yeah. Let's go and plug my calculator in. I don't think I did. Poor little dude is almost dead. Yeah. Oh, there he is. All right. Fascinating. Oh, there we go. Remember that stuff? All right, let's get this cleared out. What is it now? 2x cubed?
Plus x minus 2.
Okay. Let's hit zoom 6, and then we're all on the same page here, right? So that definitely looks like the answer is not going to be rational. It's definitely not a whole number. You guys see that? Because it's not quite at 1. It looks to be. Yeah, it's not 1, is it? No. So how do I find this? How do I find this answer? Does anyone know? Calculator costs enough money, right? Shouldn't it be able to do that? Yeah.
Just go to
Yes.
second trace.
Good. Well, not. Oh, sorry. Yeah. Second trace. To get to calc, you want to calculate something.
Click on number 2.
Yeah. I want to find a 0 of the function, right? And then here's what's interesting. Pretty sure we did something like this earlier this semester. What's the question it's asking right now?
On the left
It wants a
side.
left bound. It wants an area in which to search, to cut down its work. Does that make sense? We're actually going to learn, so now it's coming back to me. In section 4.8, we're going to learn the exact thing the calculator does to do what we're about to make it do, right? So let's give it a left bound. So am I on the left side of the answer?
Yeah.
Yep, so hit enter. Now I want to move over to the right side of the answer. Hit enter. So you see how it's going to look between these two things? See the little triangles? Then I want to give it a good guess. So that's about as good as I can get, about right there. There you go. 0.835, blah, blah, blah. We would never find that By hand, yes? Okay. Maybe? So again, you should be curious. What the shit? How does it do that? What does it do? Right? You should be kind of curious. Is anybody at all curious about that? Or do you guys like, it's a magic box? Right? It's like some Hogwarts shit. Just leave me alone. We're gonna actually see what it does. You're already looking at the clock. So coming back to this problem, what does this mean? What does this mean for us in this problem? Anybody?
It's
So now we know the x, it's 0 when x is 0.835 roughly. Sure. Right, and again, I could do this just to make sure that this is going to be, we're trying to make this a minimum, right?
yeah.
All right, so if I put a 0 in here, this would be negative. Is that cool? And if I put a 1 in here, 2 plus 1 is 3 minus 2 is positive, so does that tell me it's a minimum? Yes. So what is the point? This point right there, that is the closest this function gets to this point, is the point 0.835 comma what? Plug it in. Somebody help me out. 0.835 squared minus 1, all right? You guys follow? We wrote the answer. It's one of the first things we did. There's the answer right there. There it is. There's the answer. All we had to do is know what x was. I don't know. What do you guys think?
Negative 0.303.
303?
Yeah.
Oh,
Does that kind of match up with how I drew this? Yeah, maybe. Yeah, a little bit. Sort of. Yeah. Wasn't exactly the best graph in the world. Yeah. This kind of graph right here, you do not have to be super detailed because that's not the point of the problem. But I just draw a quick little sketch just to kind of get a concrete idea of what's going on, right? Okay, maybe. So I'm sorry that one had some more involved stuff, but I had a couple reasons I wanted to review synthetic real quick, and then I wanted to show you how to make the calculator do it, which leads right into the next section for us, which is awesome. Okay, so let's do one more example of an optimization problem. Sorry. Something interesting was happening. And then we'll do a little bit of the next section, then we'll call it a day. Now, you know, as a student, what will suck about this section, like any word problem section in any math class, is that they each will have their own little thing happening, right? So when somebody says, just tell me how to do, I'm like, it depends on what they say in the problem. You have to be able to model what they're saying in the problem. So I'm trying to give you a few general categories you're going to see, right? There's going to be some where you want to draw the rectangle and blah, 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 just like we did the first one. There's going to be some like this one. I had one in mind. What was it? Oh, yeah, I have it. And then there's going to be something, oh, yeah, okay, you're going to, okay. You're going to love this. What is the largest rectangle that can be inscribed in the ellipse x squared over a squared plus y squared over b squared plus 1? Yes?
Do you mean like area?
Yes, I love it. What is the largest area rectangle? It's bad grammar, but yeah, okay, that's a good one. What's your immediate reaction to this? What's any immediate reaction to this? What part of this is giving you the most hives, heebie-jeebies? All right, good. All right, it's this word inscribed. Does anyone know what that inscribed means?
Inside of the.
Yeah, so if I had a triangle, so there's actually a problem in the homework that's, I don't know if I assigned it to you, but it said a circle inscribed in a triangle, equilateral triangle. So it should touch each side. So this is an ellipse. Can anybody tell me what would make this a circle?
Taking away a squared and b squared. Getting rid of a squared and b squared.
Sort of. If a squared and b squared were the same. So if a squared and b squared are different, isn't it acting different in the x and the y direction? Wouldn't that make it either like this or like this? If I make a squared and b squared the same, it should be equal in the x and y direction. That's what a circle is, yes? But the minute I make a and b a little bit different, now I either flatten it this way or flatten it that way. Maybe? What would make this a hyperbola? If I make one change, this is a hyperbola. Minus here. Exactly. I like it. So let me do one thing with you real quick. Today is like review in a way. Aren't these both positive numbers? Right? Because we're not using complex stuff. If I have two positive numbers that add to be 4, can somebody give me an example? Two positive numbers that add to be 4. 2 and 2? 1 and 3? 0.5 and 3.5?
Oh my god.
Yes? 0.17 and 3.83? Right? Do you see how that's contained? Can that just go crazy? No, whatever one is, the other one, it's contained. Now, give me two positive numbers that subtract to be 4. 8 and 4. 5 and 1. 106 and 2 and 102, right? Is that contained? Or can that go crazy? I really want this to make sense. Why is an ellipse closed? Because of what we just said. If I add two positive numbers to become something, in this case 1, right, in the equation, it's contained. If one gets big, the other one's got to get small. If I say the subtract to be something, if one gets big, the other one just needs to get big, right? So that they stay the same distance. So now I can go to infinity. Yes, maybe? Okay, I don't know. All right, this is looking like trying to get you into the Illuminati or something. Okay, go. So draw this. How would it look? We have to make some assumptions, right? So let's just draw it. And the nice thing is, well, I won't say too much. I don't know if you remember what A and B tell you. What does A tell you? Does anyone remember?
Is it squared?
Sure, but what does A tell you? What's the biggest x can be? Can somebody figure that out? What is the biggest x can be? In order for x to be the biggest, what must be true about the y piece? Smallest. And what's the smallest this piece can be is 0, yes? So what would x be in that case? A, there it is, right? And what do you divide by a squared to get 1? A squared. So x would be a, yes? Or negative a, because it's squared, right? So a, since it's with the x, is how far it goes in the frickin' x direction. So what does b tell you? How far it goes in the frickin' b direction for the exact same reason, yes? Is this coming back a little bit? You guys remember graphing the ellipses and blah, blah, blah? This is the semi-major and the semi-minor, actually blah, blah, who gives a shit? All right. So I'm just going to kind of draw it, assuming it's like this, but it could be like this, but who cares? You just draw something, so I'm going to draw Stewie's head. It's like very sad on him. Sorry. Okay. Again, see, it doesn't have to be beautiful, does it? Can you now inscribe a rectangle in there? There are many ways you could do it. Do you understand? If I did it here, wouldn't that be like really skinny and long? So let's kind of do it like here, maybe. That's inscribed, yes? It touches each corner, touches the thing it's living in. Okay. Love you guys. Now, here's something interesting that will happen on a lot of these kind of problems. This inscribed kind of problem. This sucks, but here's something interesting. I want to make this the biggest area I can, correct? Can anyone tell me what's true about the area of each of these pieces here?
They're the same.
Yeah, it seems like they should be equal. So what? This is something interesting. Can't I then, if I make this one as big of an area as I can, wouldn't that make the whole thing as big of an area as it could be? I really want this to make sense, because if I try to look at the whole damn thing at once, it gets kind of gross. All right, so let's focus on this piece. Let me draw it over there. You gonna work? Yes. Okay. Let me draw this. I'm just gonna focus on the. So what do I need to know to figure out the area of that rectangle?
Area under the curve.
Get ahead of me. That's chapter 5. I don't have to know that though, no. And to know the area of any rectangle, what do I gotta tell you?
The sides.
Side lengths, right? So how long is this side? Almost by definition, how long is this side? That's right, it's x. And how long is this side? Y. And we can be better than this. Can y be anything it wants to be? Doesn't it have to be the y that goes with that x? Yes? So this is just like what we did earlier. Can you guys tell me what that y value is in terms of x? What do we know? What does it sit on? What does that point sit on? What is it sitting on?
Curve.
The ellipse. What's got to be true about any point on the ellipse? It better freaking work in here. So how do you tell me what y is? Don't you just take this and solve for y? Do it. Oh wait. So if a point lies on a given function, you could be more specific than saying it's x comma y. It's x comma some function of x, because it's got to live on that function. So good. How do I keep going? What do I do next?
Multiply by b squared.
Multiply by b squared. I love it. I'm just going to do this. You'll see why in a minute. Don't actually distribute that. Take a square root. And the beautiful thing is, considering which piece we took over here, square root, I normally put plus minus, but we know we're going to use positive, right? What's square root of b squared?
B.
B. Square root of this. I could do one more thing to kind of pretty this up a little bit. Bring this up here. Can I take out a over a squared? I think this is one thing you guys are just not used to working with. You're not as comfortable as you should be. Can you guys, if I want to take, see how I don't like that internal fraction shit. Right? What am I going to eventually have to do with this thing? Isn't it going to be a piece of something I have to take the derivative of? Aren't we eventually going to want to find critical numbers? Do you want to work with the current form of that? I don't either. So if I take out the square root of over a squared, isn't that a? And when I take something out, I divide it out. So I'm dividing by 1 over a squared, which is multiplying by a squared. So then I get a squared minus x. Yes?
That's kind of like an algebra-ish question. For when you take the root of b squared, you're allowed to just root like one side and then square root the other side?
I square root of this whole thing.
Yeah.
Square root of b squared is b.
Yeah.
Square root of this is there. Yeah. So what's the area of this piece then? What's the area of this?
X.
X times y, and then we know what y is. So what's the area? X times this. We write it like this. Oh man, well I can just feel the excitement. You guys are like, oh, this is the chapter, this is the section I've been waiting for. Oh, this is gonna be so exciting, Jeff. Oh, I'm gonna not do this and hope you don't notice. No, don't do that. So again, what's important here is not this specific problem. What's important here is why did I do what I did, right? So you can see why I did what I did. You can do the same motivation will apply to each problem you look at. That's the hardest thing. It totally is. It's the hardest thing, right? Because you guys want to like memorize the steps of this, but will that make any sense? No, because you're not going to see another problem like this. They will be a little bit like this. Yes, I did this evil laugh. They'll be a little bit like this, but it won't be exactly like this. So memorizing this shit doesn't make any sense. What's more important then is, why did I do each thing I did? Yes? So what the hell do I do with that now? What's the whole point of this question? We want to try to find a maximum area, right? So what do I do with that? I'm finally in section 4.1 again.
Derived.
Can you use a graphic calculator?
No. Good try. Derivative, yeah. So you can find the critical numbers because the maximum is going to probably occur at one of those, yes. Are you excited to do this guy's derivative? That's right, we are, okay. I'm going to take this away here. I'll do it with you, all right. It's not as hard as it looks. Don't you have this function and this function, yes? So what's the main thing happening, the main rule? Product rule. What's the derivative of b over a times x?
B over A.
All right, that first shit is easy. Can't write it, Jeff. There we go. Plus bx over a. Now, how do you do the derivative of stuff to the 1/2?
Bring the 1/2 down.
1/2 down. In front of this. Now it's to a what power? Negative 1/2 power, and then you multiply by
The derivative of the
derivative of the inside. Okay. Right? It's not. It was not hard. Especially because I did it. But I mean, you know. Right? There's A's and B's. Who gives a shit? They're just constant, so we can do this. Now that is kind of gross. Let's kind of clean this up a little bit. B over A squared minus x squared to the 1/2. Let's see. The 1/2 and the 2, right, cancels. You guys see that? Yes? 1/2 times 2 is gone. You guys aren't reacting. I'm going to pretend like you know that 1/2 times 2 is 1. I'm going to bring the negative out front. And you got an x here, right? So it's actually bx squared. Yes? Is everybody with me? Bx squared over a times this. Okay. Stop for a minute. Oops. And of course now, we eventually want to do what with this? To find the critical numbers, we want to see two things, where it's undefined or where it's
equal to 0.
equal to 0. So what are we going to want to do with this thing?
Factor.
Factor it. Let's see. B over A comes out, yes. What else comes out?
A squared minus negative power.
Good. Smallest power you see. Now here's the beautiful thing. That's gone. This divided by this is this times the reciprocal. So 1/2 times 1/2 makes a whole a squared minus x squared. That's the beautiful thing about taking out the smallest power is it kind of makes a whole other piece almost all the time. Now this other one, what's left? Took the b over a out, took that out, so the only thing that's left is x squared. Now that was better than you thought it would, doesn't it? You're all like, sure, it looks horrific, and I thought it was going to look double horrific. So sure, it looks better than I thought it would. Let's see. Screw you. We know what we're doing. All right. So what are the critical numbers? So there's a critical number from this guy right here, because it's a negative power. And where will it be undefined when x?
Is 0.
0.
No.
It's
When x equals a. So one critical number is x equal to a. And then the other critical number is going to come from, is this cool? Right? When that equals 0, correct? Now notice this, if x equals a, what's y? Right, if x equals this one, then there's space for y. If x equals this one, there's space for y. If x equals a, is there space for y? No, it's just a flat line, right? Yes? That would minimize the area. So screw you. What's my other critical number? When this equals 0. So this came from when it was undefined, right? Because it's on the bottom. That's this critical number, and it leads to stupid shit, right? So we throw it out. The other critical number is when this is 0. So this if this is 0, what would x be? Square root, so you get a over square root of 2. So you get root 2 over 2a. Crazy shit. You guys excited? Just to cut to the chase. Do the whole number line thing. This comes out to be good. So that's x. What would y be? Can we figure out what y would be? Do we have y equals some function of x? Yeah, there we go. Somebody's pointed it out for me. All right, so y would be b over a times the square root of a squared minus x squared. You put this way. So this would be b over a square root of a squared minus 1/2 a squared. Yes? And that's 1/2 a squared. B over a squared minus 1/2 a squared is 1/2 a squared. The square root of that is a over the square root of 2. So you end up with rad 2 over 2b. That's almost too nice to believe. I mean, that's kind of neat. You guys are, look, you're all still looking up here. That's good. This is not an easy problem, which is one reason why I picked it. So what's the actual question again? Let's see. This is the last thing you do is you go back to the problem. Like, what did they ask me? Where did you put this, Jeff? I don't remember which one this was. Here we go. Blah, 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 blah. Here it is. Oh, there it is. Find the area. Okay. So what would the area be? Isn't it just, now it's not x times y, correct? Because the real big thing was how many times this? 4 times x. So it'll be 4 times x, which is this, times y, which is this. So it'll be 4 times 2 over 4 times AB. So I get 2AB. Oh my God, that's funky. That's awesome. Oh God, let's stop that. Not for today. You guys are too excited. We're going to stop with this section. We're going to move to the next section. Yes?
Is that question going to be on the test?
This one, this exact one,
Well,
never. But I could do like a rectangle and a circle or something, right? Or I could do a circle and a rectangle. I could, so just, will an inscribed problem be on the test? Almost definitely, right? There's a few of them in the homework. So I gave you several examples. You got several examples in the book, right? I don't know how many guys don't do this, but if you don't, you're insane. You go, I don't know what to do. Flip back and look at every frickin' example in the section, yes? Because one of them might be really real closely related to the one you're looking at, right? Because you eventually get to a point, if you go far enough in mathematics, I got to a point where the book was this thin and it still costs $180, and I was joking that if I ripped a page out, I should be able to get lunch at Wendy's or something. Here's the page. Oh wow, here you go. But you get to a point where I'm like looking, and then there are problems, no examples. No examples. So embrace the examples while you have them, yes? Okay. So last thing we'll do for today, you gotta get into 4-7 and try it out. Come with your questions. We're gonna do like I promised earlier, we're gonna see what exactly does the calculator do to get that answer. Okay. Everybody got what you want from this? Isn't that exciting? You know, like, get ready to use a lot of paper. Okay. By the way, real quick, didn't we just get this area of the largest rectangle? Yes? Yes? So if somebody said, okay, in this ellipse, what is the area of the largest rectangle you can make? Can anybody tell me what A is? What's A?
3.
3, good, because that's A squared, right? So the area would be twice A, and what's B? 4. So the largest rectangle that could live in that ellipse would have an area of 24 whatever units, right? Yes, maybe? And so you just know that. So if it comes up on Jeopardy, you got it. Okay. I know y'all watch Jeopardy. So, last, real quick. So in section 4.8, this is the section that talks about the algorithm that the calculator uses to do this. And it's called Newton's method. Right? Newton just, really had too much time on his hands. He did a lot of shit. He just had apples falling on him. He did some other stuff. Right? This is I remember learning this. I know I'm not your standard person, but I was just fascinated by this. So if I'm given a function, and it does need to be well behaved, it doesn't have to be continuous and differentiable everywhere, but it just has to be, I'll show you in a minute. All right. So how many roots does this function do this? How many roots does this function have?
2.
2. All right. So let's focus on this guy. Let's focus on this root. So the whole point of this is, how do I find that root by hand? And then somebody might say, oh, you're a calculator, Jay, you make it. But didn't somebody have to program the freaking calculator? Because it isn't actually like a little magic wand in the calculator, right? So, here's what's really cool. If you try to find this root, right? Let's say that we know, let me not make this specific. Let's say that, all right, let me just build this and then we'll talk about the problems. Let's say that x1 is our guess. X1 is pretty close to that root. That's our guess. So this is really cool. Notice something. If I draw the tangent line to that point, does the x-intercept get closer to the root? Yes. Would it do that for any guess? What if I guessed this? Would that tangent line get me closer to the answer? No. So again, this just has to be continuous and differentiable close to the root you're interested in. So it could do all kinds of weird shit over here. It could jump around. It could do all shit because I don't care because it's not close to the root of the one. It just has to be nice, close to the root. And your first guess, if you don't get close enough, it could just make the whole thing go insane. Which explains why this dude is like, give me some frickin' idea of where I should be looking, right? Does that sort of make sense? Maybe? No. Again, if I made my first guess this, then that tangent line would take me further away from the answer, yes? So that wouldn't be a good first guess. Okay, so this would be then what we call my second guess. And isn't it better than the first guess? How would I improve that second guess then? I would do the whole damn thing again. So I'll calm down a bit. So here's my second guess, and it goes right there. So if I draw this tangent line, that would be my third guess. Look how close we're getting now. You guys see that? We're getting closer. Now, right now, I know you're all out there saying, what this shit am I this is going to look like? What actual work do I need to do? Since I keep doing the same thing over and over, we can set up an algorithm that we just kind of will be able to put in the calculator, hit enter, 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 and then we get there. That's what we're going towards. This is easy to program because it keeps doing the same thing over and over. And what is that thing? So let's back up. Let's go back to, here's our first guess. This red line, what is it? It's the tangent line. Right at x1, f of x1, yes? Is that cool? How do you find the tangent line to a function f of x? What do you do? And again, if you want to, you can think of it in terms of linear approximation, because that's what a tangent line is, right? So you can, now you can think of it either way you want to. So isn't f of x approximately f of a plus f prime of a, x minus a? What is my a? What is my a that we're using? x1, right? x1 is the a that we're using. Okay, so let's be more specific. F of x is approximately f of x1 plus f prime of x1 times x minus x1. So that is my tangent line, correct? All right. What did I do next to get x2? I took my tangent line and I figured out where what? What did I find? How did I get x2? I took my tangent line and I figured out where it's the x-axis, otherwise known as the x-intercept. How do you find the x-intercept? You make what? Set what equal to 0? Y. Good. So set this equal to 0. Put it up here. So I really want this every step to make sense. Visually, this is kind of beautiful, even though I suck at drawing. This is still not bad. Take a guess that's relatively close to the actual answer. Tangent line. Get the intercept. Now you build another tangent line based on that new number. Find the intercept. Then you would do it again. And you keep getting closer and closer and closer, right? All right. What do you think I want to do to this to get what x2 is?
Take the derivative.
No. How do I, let me just solve for x. All right. You want to know what x value makes this work. What x value makes this 0? Isn't that what x2 is going to be? Is the x value that makes this 0? So let's solve this for x. Subtract this guy. Divide by him. add x1, right, so I get this. So we're gonna call this x2. It is the x-intercept of this tangent line, but what do we then use it for? Our second guess. And it should be better than our first guess. And then, so what would x3 be? So what would xn plus 1 be? The n plus 1th guess. xn minus f of xn, I like it, over f prime of xn. Good Lord, Jeff. Yeah. This is the algorithm. So we can put this in the calculator in a certain form and then just make it do it over and over and over again, right? So let me do this. I'll give you this sheet. Next time we'll do some examples, but I have the sheet that's got a couple of examples. It's got the actual algorithm written by a computer, so you can actually read it instead of whatever the hell I did up there. I already gave Carmen hers, so don't worry. There's a second sheet that just had one, anyway, stupid formatting, I love it. Don't worry. So, I mean, do you see at the top, I've got the general xn plus 1, right? If you want to look through this, go ahead, but next time we'll do some examples of this. So this Friday, we'll finish up chapter 4. I'll have the practice test for you because the test is going to be when? I think it's next Wednesday, correct? Yes. So Monday will be review day. I love it. Okay, so let me know if you have any questions. Otherwise, you're free